Yeah.
Okay, everyone, thank you for joining us for today's University of Texas Energy Symposium for March 7th, 2023. I'm Harry King, Assistant Director of the Energy Institute and Research Scientist here at University of Texas. Before I introduce today's speaker, and point out the next two talks. There will be no talk next week, so that's spring break. The following week, March 21, we'll have a talk from Stuart James from Germany, the Deggendorf Institute of Technology, talking about open source data for understanding the energy systems. And then March 28th, we'll have Sarah Jordan from now at McGill University, and she's going to talk to us about life cycle assessment of energy technologies and understanding life cycle assessment in the context of climate change or energy transition. But today it is a pleasure to have with us Dr. Peter Eichhubl from the Bureau of Economic Geology, and senior research scientist there in the BEG, of course, part of the Jackson School of Geosciences here at the University of Texas at Austin. So we're going to hear about storing hydrogen in the subsurface. So his research is in the area of fault and fracture mechanics, low temperature geochemistry, addressing deformation mechanisms in the upper crust, structural control of mass and heat transfer, and sedimentary basins. Mass transfer, as the rest of his biography here, is essentially an expert on the subsurface and how things move around in the subsurface. Perhaps nothing, well, I guess he will tell us if maybe nothing is more challenging than hydrogen in the subsurface. Maybe we'll learn about the particular challenges of hydrogen versus modeling and tracking other kinds of fluids and gases in the subsurface. And so that's what his talk today is going to be about. How do we store hydrogen in the subsurface for various reasons, which he will go over. So a lot of hydrogen this is abstract, discusses here, is trucked around in pipelines and tanks. For long-term storage, we probably think maybe we need to store it in the subsurface, seasonal storage over the course of many months. And so this is similar to natural gas storage that we already do in the subsurface on a regular basis. And so he'll give us the analogs and tell us what's different. So we're going to learn something about geology today. For everyone online, as usual, send your questions in on Zoom, question and answer feature. And if you're on YouTube, submit a question there, and I will try to ask it to Peter at the end of his talk. So with that said, I will now hand it over to Dr. Eichhubl. Thank you.
Thanks, Karen. Thank you for giving me the opportunity to present to you all. Don't worry, I won't give you a geology lecture, but it will have a fair amount of geology in it. But overall, this is a very interdisciplinary topic, and always a little bit of a challenge because whoever's presenting this, my background is in geology and the subsurface storage aspects of hydrogen, but obviously I'm going to try to give a wider overview. So it is implied that I talk about hydrogen that I will go into areas that I'm not so much an expert on. Okay, so recognize that, and this will apply to any hydrogen lecture you get. Maybe an engineer talking about certain aspects, and then there's chemistry side, there's engineering side. So there's many aspects of the topic. So the purpose of this presentation, there are kind of threefold. The first one is just to give a very generic introduction to the role of hydrogen for the low carbon economy. The second objective is to talk about storage and subsurface storage, in particular of hydrogen. And then the third part is, I will give us very short at the end. I will move quickly to the last part. Introduction of our research group at the Bureau of Economic Geology and Cochrane School of Engineering that works on those topics. So the last part will be a little bit more more detailed geology stuff, but just to give you a flavor of the kind of research. Obviously, that's a little more specialized because we're trying to go into new areas, right? So, a quick primer on hydrogen. It is flammable gas at atmospheric conditions. It's non-poisonous, light in air, disperses quickly, and is currently used as a feedstock for refining, oil refining, natural gas, plastics, ammonia, and as a fuel, and either as a compressed gas or in some cases cryogenic liquid. Remember, well, you may not remember, but some of the rockets that go to in the past part of the program and some of the NASA programs, they use liquid hydrogen as a rocket fuel. It is energy dense by mass, but not by volume. So there are pros and cons compared to gasoline and natural gas. So compared to gasoline, the energy of 1 kilogram of hydrogen is about that of a gallon of gasoline, which happens to be, I have to look it up, 2.7 kilogram. But compared to natural gas, same volume, it only has a third of the energy. So you need much more space to store the same amount of energy compared to 3 times the space compared to natural gas. The reason we're talking about it, the main reason, maybe the only reason, is that when we use it, it does not release CO2, right? So it's a CO2 carbon-free energy carrier. And which does not mean that there may not be any CO2 emissions involved in producing the hydrogen or transporting it, but when we consume it, there are no emissions. The advantage of that is it may be easier to collect the CO2 that's being emitted at the source. So you don't have it come out of the tailpipe, for instance, right? So there may be CO2 emissions with generation transport, but not at the end use. There may be NOx emissions when it's combusted, which you can avoid by using a fuel cell and generate electricity. And hydrogen is also considered a greenhouse gas, actually. So you don't want to leak it into the atmosphere at large quantities. So the term that's used here is low carbon intensity hydrogen to make sure that there's no misunderstanding that even what we call green hydrogen, I'll get to the next slide, is not necessarily carbon emissions free. Oh yeah. So the other thing to keep in mind, if you come from the petroleum side, as I do, many of us, it is not an energy source. It has to be generated. And there are different ways of doing this. There is natural hydrogen occurring, but it's not known to be in quantities that would be useful. So I'll get to this. So source of hydrogen, this is arranged, let me use this one here, arranged from the left to right at lowest CO2 emissions to high CO2 emissions, which comes, unfortunately, the trade-off of highest price to lowest price. Ideally, hydrogen is used by electrolysis, using wind or solar or hydropower or maybe geothermal at some point. So carbon emission-free electric power. It could be done in conjunction with nuclear energy. It can be produced just from the grid, and whatever the grid is being sourced, that's the energy mix that comes out of the grid. Commonly, it is produced from natural gas today by steam methane reforming. And today, the CO2 that comes out of this process is released in the air, but that CO2 could be captured and stored. So there's the option of with or without carbon capture and storage. There is an option also to use pyrolysis, which produces solid carbon, which actually has a value to it. So this is a technology that's available, but would have to be implemented at larger scale. And then at the lower end here is coal gasification without carbon capture. So that's the cheapest, but high emissions of CO2. So obviously our interest is in the low emission aspect of this, but the cost currently is high, and the target is to bring this down to $1 per kilogram of hydrogen. So that's the technology challenge here. Current hydrogen production worldwide, 70 metric tons per year. And you see this is mostly by steam methane reforming out of natural gas, coal, and just a small percentage by electrolysis. US production is 10 mega metric tons. And remember this number, I'll get back to this in a while. Less coal, but the same small abysmal amount created by electrolysis. In comparison, natural gas production is 1 to 2 megametric tons per day. Okay, so we produce in 10 days we produce as much natural gas as we produce hydrogen in a year. Okay, so if we want to substitute one with the other, we have a long way to go. That's the same what I just presented in a different graphic. So this is the flow of world hydrogen production consumption. Those are the sources on the left, natural gas, coal primarily. And on the right is the uses, refining. Ammonia takes a lot of that. Methanol, very little goes to transport. And then heat and other sources. So predominantly it's a feedstock, okay? Not so much an energy carrier for other applications. Now, I mentioned already that hydrogen does occur naturally, actually. It's not that it's rather abundant, actually. So in the atmosphere, 0.5 ppm, that's not so much, but there is what we call primordial hydrogen that's created by the creation of the Earth. It's in the core of Earth and the mantle. And it's produced by chemical reactions, with biogenic or abiogenic reactions. And it is in natural gas, typically less than 10 more percent. In some rare cases, more. And there's one location, is this one here in Mali in West Africa, where it's actually 98%. So that's the only known that I'm aware of, the only known natural accumulation of hydrogen where you can drill a well and produce it. Other than that, it's not considered a natural resource. And this map here shows discoveries of hydrogen at more than 10%, more percent. And this map shows one thing. There's a heavy bias towards certain areas where people looked for it. Okay, the Russians have done a fair amount of analysis. It's obviously where oil and gas occurrences are, but this is not representative probably of the actual distribution of hydrogen accumulations. So this is something that needs to be worked on. If this is something we consider, I mean, then the downside of having drill rigs again, and exploiting subsurface resources. So maybe we want just to avoid this altogether, but something to keep in mind. Okay, the reason we believe there's not more of this, even though it's produced by the Earth, but it's also very reactive, and microbes like to eat it. They like to convert it into methane, for instance. It would go, if there's hydrocarbons there, it would go into the oil phase. There are mineral reactions where it would be consumed. So it may be not so much, there's not enough hydrogen being produced and coming toward the surface, it may be consumed very rapidly. Again, something we don't have a good control over. So how does hydrogen fit into this low carbon energy future? The prime focus is on electric power from renewable sources, solar, wind. Other options are geothermal, which is something I'm also engaged in, but I see some significant technology hurdles there. Biofuels, hydro, maybe it kind of maxed out, the opportunities for more dams, hydropower. Nuclear, you may consider it as a low carbon, yes, but not necessarily green, so that's, well, don't want to go ahead with this. Electric is not so great for certain applications, aviation, putting batteries in the plane. It is also, since it's used as a feedstock, we do need hydrogen. Storage. With electric power, we have batteries for short term. I'll get to that more detail. We have pumped hydro for long term. Again, limited. It's already existence. Building more dams, damming up rivers comes with downside. So the problem with especially solar and wind is they're intermittent. So we need energy storage for that to even out short and long-term variations in supply and demand. And hydrogen could play a role in this. So provides an opportunity to replace what we use natural gas, for instance, today to a large extent. So energy storage is perhaps one of the key applications for hydrogen. So this is a graphic that UE has put out, which puts together how hydrogen can be used. I have a list here on the left here that there's some of the advantages of hydrogen. Low carbon emissions because it's by itself carbon free. It's transportable as a pipelines, just like natural gas. You can truck it in a tube trailer. You can move it as a compound, ammonia, which can be converted back to hydrogen. And ammonia itself is a feedstock. It can be stored in small to large quantities. Long duration storage, which is a problem with batteries, I guess. I already mentioned that we have multiple sources for it, and we have multiple uses. So this is synthesized in this figure here, where in the center is hydrogen generation. On the left is the grid, the electric grid. On the right is the hydrogen itself. And then we have on the left side here the various sources of hydrogen, renewables, nuclear, fossil fuels, fossil natural gas, ideally with carbon capture and storage. Then we have on the right side, we have the applications, transportation, synthetic fuels. So synthetic fuels, you would use CO2 and combine it with hydrogen and have the potential to create aviation fuel that would obviously emit CO2, but that CO2 has been captured before. So that would be carbon neutral, right? That's the idea. You could use this to upgrade produced oil by grading it. I've already mentioned ammonia. Metals production, we do need natural gas present day to reduce it. You could use hydrogen. Various chemical processes, and then heating and distributed power. So you see here, this goes an arrow back to power generation, then the grid, and then more hydrogen generation. So it can go back and forth. The nice thing about hydrogen, I put this down at the bottom here as a reminder for me to mention, it's very important, because it can play so many roles. It's very flexible in its use. So it could play a role initially when we rely heavily on, say, natural gas, steam methane reforming, the CCS. But then down the line, as we shift the energy mix away from natural gas to more renewable electricity, solar and wind, the hydrogen can go with it, right? So it's not specific to one source. So it's very flexible, which is good to have, because if you invest into it, you can be assured it would be a long-term investment, right? So it goes with the change energy mix, the hydrogen would be a relevant carrier. There are various forecasts for hydrogen demand, and I don't want to go into too much detail because I'm not the true expert to talk about it. And what those models differ based on the assumptions they make. The fundamental assumption here is carbon neutrality by 2050. That's the idea, but there are different ways of getting to it, and then what role hydrogen plays is various. So there are two models here, one from NREL, the other one is published by the Fuel Cell Hydrogen Energy Association. They come up with different numbers by 2050, but this one here, the different scenarios, base scenario versus ambitious scenario, 60 metric tons per year. And now remember that what I said, present day US is 10, so it's a 6-fold increase. They have a somewhat lower numbers here. So this is demand supply, but and then it's broken up for the different sectors where it would be either used or produced. So there are a lot of different models, and then other ones that MIT is working on one right now as we speak to come up with revised numbers. But kind of the bottom line is it would take a significant ramping up of production, 6-fold in this case. Very important, demand and supply have to grow at the same time, right? You don't want to create a lot of supply and then have the one who's buying it, and vice versa. So that's the trick. If you don't have, other than feedstock right now, but you don't have massive use of hydrogen for energy production, for instance, right? So that has to grow at the same time. The way of doing this is to focus on parts of applications where there's not much of an alternative besides currently natural gas and then hydrogen. So for instance, I mentioned steel already. Interstate transport may be one, long distance trucking, seasonal storage, I will get back to this, and I mentioned the synthetic fuels for aviation. So focusing on what we call hard to abate sectors, where otherwise it would be very hard to get rid of the carbon emissions. That's one way of doing it. And then so much focus is in this discussion on emissions, but I would say that's not the only driver. When people buy electric cars, they may think about emissions, but they also buy those cars, I believe, because they're fun to drive and they like the technology. So other reasons besides the emissions. The emission reduction, that is what allows the government to give a subsidy, right? But at the end, people may adopt the technology because they like it for other reasons. You know, it could be emotional, it could be because it allows them for a company to project a green image, right? So a variety of reasons, and I think that needs to be considered as well. So focus on technologies where there would be an advantage besides the reduction in carbon emissions. Now, a few words about resilience. Here in Austin, we are experts on electric power resilience. We have experienced it twice in the last 2 or 3 years that people were without electric power for 10 days. It's good to have alternative technologies besides depending on the electric grid. And hydrogen, to some extent, can do that. It can be pipelined, it can be trucked, it can be stored. It's not going to work without electricity, though, you know, so let's not fool ourselves. You can't produce it without electricity. So, but it may add more resiliency to our energy supply if, as a, in addition to electric power grid. So, you know, hard to quantify that, what it's worth. But the storage aspect obviously goes into this as well. We'll talk in a moment about seasonal storage, but there's also long-term strategic storage. We have currently a national petroleum reserve that was used recently to even out the spikes in the petroleum cost. Well, if you have long-term hydrogen storage, that could play a similar role. There are some disadvantages of using hydrogen. The one I list first here is, I already mentioned this, the low density by volume. So it takes a lot of storage space or not just storage, but if you want to move it, you need a lot of space for that. It's has high volatility. And I will talk about security and safety in those moments here. But it burns quite easily. Also, it's a downside. It is inefficient to convert it back into electric power or from power to hydrogen. So you don't want to do this too many times. If you don't need the storage aspect, maybe you just use the electric grid to get the electricity generated at the wind farm to the consumer, and don't worry about hydrogen. You just have losses, right? Pipeline transport, even though we can move it in pipelines, the compression cost is 3 times that for natural gas because it's so low density. You have to do more work to compress it to the same pressure as natural gas. So it's just pure physics. It may react with steams. Okay, so if you want to use our existing pipelines, or especially for home use, not so much the interstate pipelines, but if you want to put it into homes, you cannot just replace natural gas with hydrogen. You can mix it up to 20%, but that's the volume, but that only gives you a quite small benefit in terms of greenhouse gas emissions, only single digits. I mentioned that it's a greenhouse gas, and burning hydrogen creates NOx emissions. So you can burn it in a turbine, you can even burn it in a combustion engine, but that creates emissions. You can use ammonia instead of hydrogen, which has certain advantages, but it's also very poisonous. The figure here shows the the energy in gigajoules per ton versus per cubic meter. And gasoline is by far the king in this regard. It's high up there, highest energy content per mass and per volume. And you probably can't read this because it's vertical, but compressed hydrogen is down here. So it's not, doesn't look good, but batteries are down here, okay? So it's still better than batteries, that's in that, so per ton per volume. But ammonia, for instance, is in the middle here. So if you convert hydrogen to ammonia, you have certain advantages in terms of its energy density. Now, why do we need storage? Obviously to even out variations in demand and supply. And that can be daily. So there's the top plot here it's known as the duck curve. It's been around for a while. It was actually a prediction, but now it's so old that it's no longer a prediction. What it shows is the daily variation in supply and demand, or excess supply and then excess demand in the evening with wind and solar. And this is for, I guess, for California actually. But so there's during the day you have excess production, solar, sun is shining, and in the evening when everybody goes home and turns on all the appliances, you have an excess demand. So you need some storage for that. And batteries can do this. And then you have similarly seasonal variations. So this is calculated, assuming that California would be powered by 100% renewables. So you have in the summer a surplus, and in the winter you have a deficit. That's where seasonal storage comes in. Batteries can go a long way for short term. So for instance, Burkhardt has this Revolution battery storage facility in West Texas. I think it's in the I don't know if it's online already or in construction, 450 megawatt. That can produce enough power for 30,000 homes for 2 hours. So that's a tenth of Boston, roughly. Okay, so, short term, yes. People are also talking about distributed battery storage. If you have your cars plugged in at home, it may actually charge, but also put back into the grid. People are having batteries at home. And works nicely for short term. Long term, not so much. So that's where perhaps the hydrogen comes in. This is a plot that shows discharge duration on the x-axis here in a kind of logarithmic, so it goes from seconds to season, and discharge power. So short term, there's a capacitor, flywheel, okay, batteries. And then there's pumped hydro here, but you see that for long-term high energy storage, hydrogen is, the way to go apparently, according to this. This is Enron here. They don't know what they're doing, and I'm not sure if even if it needs to end here, it could go beyond seasonal, could be multi-year. Again, I mentioned the National Petroleum Reserve, so this would be a multi-year storage. And with oil and gas, you can always idle a well and then resume production when you need it. With hydrogen, you probably can't do this because you have the infrastructure in place. It needs to run. The windmills are running. If the wind blows, why would you idle it, right? So, and also we can store the oil in a reservoir in the ground. The electricity we can, so that's where hydrogen comes in. So hydrogen for seasonal, maybe monthly to seasonal, not necessarily shorter than that because the compression costs and and then you have to clean it. There may be downsides to it really short term. But it's really, they go down to actually here, the green goes to hours. I'm not sure if that's justified. I would stop here somewhere by weekly, Okay. So different storage technologies. The first ones listed here are surface storage. So this is spherical vessel, pipe storage, pre-stressed concrete. Then so this would be compressed gas, then cryogenic. There are two forms: liquid hydrogen and cryocompressed hydrogen. So liquid is just making super cold at minus 253 degrees C. With cryocompression, you use pressure and low temperature, but you don't have to go so low. And then geologic. So that's all compressed gas. There are 3 or 4 options here: salt caverns, lined rock caverns, and what we call porous reservoirs, which are either depleted oil and gas fields or saline aquifers. And they have different pressures, operating pressures, and different working capacity, vastly different. And the next plot here shows this much better than the table. So the surface options are those here, and the geological options are those here. So this, if you really want large quantities, then going to the subsurface is the way to go. Okay. So let's talk about, that was the general introduction to management, I guess. Now we talk about subsurface storage. As I said, large capacity, long term. You won't see much at the surface. There will be a wellhead and maybe some facilities to purify it, but it's outside. I mentioned that those 3 or 4, depending on how you count. All those storage options are in use for CO2 or methane or other materials, not necessarily for hydrogen, with the exception of the salt caps. So overall, we have a lot of experience in storing fluids in the subsurface for 100 years. And this cartoon here, those are the salt caverns here. This is a salt is very mobile in the subsurface over geologic time scales. It flows like a liquid. So it forms diapirs. They move up because they are less dense than the rock. So they form those bodies where you can, the salt caverns are produced by a solution leaching. So you drill a well and you pump water in, the water dissolves the salt and forms a cavity. Those things here are supposed to show a depleted oil reservoir in red, and what we call a saline aquifer. Saline aquifer is the same thing, except you don't have any oil or gas. The pore space is filled with water, and typically that water is not fresh water, it is saline, so we call it the saline. But the rock would be the same as is the oil and gas field. And you obviously would go to a depleted oil and gas field because you would first produce the oil and the gas, and then you would go back and store hydrogen. Now, where you would use which type of storage depends on the geology. You can do all of those types wherever you want, because you may not have salt layers in the subsurface where you can form cavities. So the green shows on this US map here shows where you have salt layers where you could form salt caverns. But you see it's only a fraction of the country. The red are areas of oil and gas production. And again, in certain areas you have it, in certain areas, the Western US, except for California, you don't have any. And then saline groundwater is the most abundant type of storage, subsurface storage medium. But again, Western US, not so great. So that control by geology is actually also shown on this map. It shows natural gas storage sites, color-coded by salt domes, depleted oil and gas fields, and aquifers. And you see in some areas they use preferentially aquifers and others salt domes. That's because the geology dictates that. Okay, so there's a geographic preference for one or the other, but it can be used in a complementary way. Pros and cons of geological hydrogen storage. So the pros already mentioned: unlimited capacity, most cost effective for long term. It doesn't matter how long you store it for the most part, whereas with cryogenic storage, you always have to chill it, right? So, and with surface tanks, you have to maintain the infrastructure. So this is, in terms of long-term storage, it's minimum cost, and it's safer than all the other surface storage options. But there's a downside. In the subsurface, you don't really control so well where the hydrogen goes, so you lose part of it. Some gets contaminated by reactions. It may turn into methane. There's hydrogen sulfide. So there's contamination. It needs to be cleaned up. The working capacity, that means the difference between what you put in, what you get back out, is not as good as with a surface tank. So you have losses. And you need to plan the well geometry, how you produce it, the production injection approach. You have to plan that to maximize the output. And then the limitation of the subsurface geology, which you cannot control, right? You can only go to a different location, but then you have to get the hydrogen. This is pretty detailed. I'm not sure I'm going to talk about it. So this is just the different types on the left, where they have currently used the status. So for salt cavern storage, we have 3 sites in Texas, 1 million. The depleted oil and gas fields, we don't have any that is 100% hydrogen. We have used hydrogen natural gas mixes in those fields, but not pure hydrogen. So this is something that needs to be tested. So salt is the most proven technology, but limited by the occurrence of salt. Also, the mining of those caverns creates a lot of brine that needs to be either disposed or used, limited size. Let's see, between depleted oil and gas fields and saline aquifers, there is the advantage of the oil and gas field that you know because you had initially hydrocarbons trapped in the subsurface. You know there's a good top seal, and the hydrogen is more buoyant. So if you don't have a sealing layer, the hydrogen will just escape. But in the oil and gas field, oil and gas is also buoyant. If it was there in place for millions of years, then the hydrogen would probably stay for millions of years, right? With the saline aquifer, you don't have that guarantee. The downside, however, of the abandoned oil and gas field is you have a lot of well bores and their leakage pathways, especially if you don't know what the condition is of those old wells, the casing, the cement that was poured in. There's always a risk to that. So that's something that the saline aquifers don't have to worry about because nobody drilled into those before, presumably. Well, so this map shows the 3 sites in Texas where currently we have salt dome storage. That's a cross section here that shows those caverns. They are typically tall and narrow, but very tall. There's a figure which I don't use, but you could put a high-rise building into those. So they're really tall structures, but because of the way the mining proceeds, it's rather slender and tall. But you can have multiple caverns in the same salt body. Currently 8,000 tons, but for the building of a storage facility in Mississippi, that will be 10 times as big, just more caverns. Okay. Porous meter storage, depleted oil and gas fields and saline aquifers. Because the hydrogen is buoyant, you need to have kind of a domal structure where the buoyant hydrogen would pool underneath. So if it is just a flat layer and if the layer is tilted, the hydrogen would just migrate out and would be gone. So you need to have a suitable geologic structure where the hydrogen would remain in place, and it needs to stay close to the well bore where you inject it into because you want to produce it out. So if it migrates away from your well, it would be out of reach. So this needs to be carefully planned. The other issue we have to think about, so especially if it is blue hydrogen, we capture the carbon at the site of hydrogen generation. And if you want to dispose of the carbon as CO2, that would be injected into the subsurface as well. And it would be the same type of reservoir. So there's the competition between sequestering the CO2 in the subsurface and storing the hydrogen. So that's something that needs to be taken into account. I already mentioned the quality of the sealing cap rock. You want to make sure it's tight so that the hydrogen does not escape to the surface. And remember, it is a greenhouse gas. So besides the loss of your precious product, you would actually harm the environment. Yeah, I already mentioned this. So there's this competition with carbon storage and hydrogen storage. Now, talking a little bit about safety here. It's non-toxic. It's an asphyxiant, so it replaces air. It is easily ignited, much faster than, so this is a table here that actually shows this. So the ignition energy is much, much smaller than it is for methane and gasoline. So those are the downsides, but some upsides are it disperses fairly quickly, especially in the open air. So if you have a leak, the gasoline vapors, they cool at the ground. hydrogen wouldn't do that. So it dilutes quickly. It burns at higher temperature, but it radiates less heat. So that's also, in terms of fire, it's less damaging, no smoke. It has a wide flammability range, which is not good. Much more so than methane. So here the range is here, ignition limits in air. That's for gasoline. Methane is the widest for hydrogen. That means a mix of hydrogen and air or wider range is flammable, more flammable than it is for methane and gasoline. So there are pros and cons, and people rank the safety characteristics as in this table here for gasoline, methane, and hydrogen. And surprisingly, we actually rank hydrogen safer overall than methane and gasoline. But it really depends what the situation is. Is it in a closed space? Is it outside? Is there an ignition source? Is there not? What is the ignition source? So you cannot generalize. But on par, I would say we know how to handle natural gas. We know how to handle gasoline. Yes, there are accidents. Homes blow up occasionally because of a gas leak. Sometimes gas stations catch fire, So I would say similar to hydrogen, just have to be careful, but it's not unsurmountable and about on the same level. This is about storage failure rate. For hydrogen, we don't know, but we do know for natural gas. And it turns out that depleted oil and gas field is the safest way to store natural gas, safer than salt caverns, for instance, or even aquifers. This is the events of this orders of magnitude, actually, orders of magnitude safer to store natural gas in a depleted oil and gas field. So this may also apply to hydrogen. And if you compare it to above ground storage, many times safer. So this number here is the number of fatalities since 1951 in the US. There are 6 in conjunction with underground gas storage. There are 1,500 with above ground storage sites. So there are many orders. Underground storage is much safer than subsurface than surface storage. There's some issues with subsurface storage here. I mentioned the cap rock, migration issues. I mentioned. Okay. Now, the problem here with hydrogen is we don't have a lot of experience with it, so this needs to be created, and we need a baseline for storage risk, and that's the only way of getting that is by doing it. Right? So a few words, and I said we'll keep this very short because this goes into great technical detail quickly. But I want to mention what we do at the Bureau of Economic Geology in conjunction with the Petroleum Engineering Department in the Cochrane School of Engineering. We have a group that is working on various aspects of subsurface storage of hydrogen. It goes from the geology, the geochemistry, geophysics, petrophysics, geomechanics, the engineering side, and also the economic side, energy economics. There are lots of options on the table for hydrogen use and generation distribution. But in many cases, the economics dictates what is feasible and what is not. So having the economist on board to keep us sane in terms of what we propose as technology is super important. So those are the 3 areas that we're working on: the storage side, the economics, and then we have a group here that works on kind of really basic science aspects. Why do we have this research group? Well, so I mentioned that we have 3 sites currently. They store about 6 billion cubic feet. The US stores 4 trillion cubic feet of natural gas. So if you want to go from one to the other, we have either we don't store, maybe we store at less extent, or we have to scale it up greatly. So we do subsurface evaluation. That's a map that shows space in coastal areas or state waters, actually, just offshore Texas. That's available for storing hydrogen or CO2. We do reservoir simulations. How do you inject the hydrogen? How do you produce it back? How does it compare with natural gas? So in this case here, there's simulated comparison of storing natural gas in a one of those domal structures versus the hydrogen. And the difference is that the hydrogen spreads out to the side much more than the natural gas. So you see the difference between this one here. So there's the risk that you're losing the stored hydrogen because it migrates away from your injection well. You cannot produce it back. Geophysics is used to characterize the structure, in this case, a salt dome here, using acoustic techniques or to monitor where the hydrogen goes in the subsurface. This is a synthetic model, but it can be done in the field using acoustic waves. This little movie, I will skip it for the sake of time, but we're looking at how the hydrogen disperses in the reservoir. It affects how much you can retrieve. If it disperses away, you lose it. Microfluidic experiments, you look at the pore scale. How does the hydrogen migrate if the pore space is initially filled with water or oil? So you want to understand the micro scale to understand the larger scale. I'm working on the risk aspects. I already mentioned that cap rock failure is key here. You don't want to lose the hydrogen either by moving up some faults in the subsurface or along existing wells. We don't want salt caverns to fail by collapsing. So this is the mechanics side. We characterize salt domes. They're not just salt, they may have impurities in it that could affect the leaching process and the storing of hydrogen. We have a large collection of ore from well bores. So people drill the well bore and retrieve the rock that's being poured out. And we have three actually, core collections at the BEG, and have a lot of ore on those salt deposits from earlier work 30 years ago. Nuclear waste. Never know. Work on something, and then 30 years later, you have different reasons to look at the same rock again. Always good to keep stuff. Never throw anything away. And then economics. So value chain analysis. How do you go from all those different sources to the demand? I mentioned already, demand and supply have to grow at the same rate. That needs to be analyzed. Cost modeling, how much does it cost to store, to filter, compress, and then filter again, and then address different storage options. The depleted oil and gas reservoir is the cheapest, so this is actually dollar amount here. I forgot to label this. Line caverns, I didn't talk about it because it's really expensive. So my last 3 slides, the Texas advantage. We're a good place here, not only in Austin, but in Texas to work on this, because Texas is traditionally a leader in energy, oil and gas, but also in wind energy, biggest producer among the US states, with a significant potential for photovoltaics. So all the core ingredients for producing green hydrogen. Water may be an issue a bit, especially West Texas. We have a lot of gas there, but we don't have a lot of water there. And you need water for electrolysis. So you may have to pipe the gas to where the water is, or the other way. Some of the oil and gas infrastructure can be used for hydrogen storage and transportation. Pipelines can be, to some extent, reused. We have the vibrant energy market and business environment. We have the people who are willing to provide the capital for new development. We have the demand centers, urban centers, Houston, with energy needs, industry. We have already the industry that uses hydrogen in refining. We have the workforce to do this kind of work, right? So the idea is if oil and gas diminishes over time, we can retrain this workforce to work on hydrogen. And we have good schools to teach the next generation of engineers and scientists to work on this. The UT advantage, UT obviously has a long tradition of energy research. Working at the Bureau of Economic Geology, half of what we do is oil and gas related, but we have a very strong Department of Petroleum Geosciences, petroleum engineering. So we have a lot of traditional work on energy and training the next generation of workers. UT already works on a lot of aspects related to hydrogen. There's a bunch of topics here. And this list is taken out of this brochure, which you can download from this website here, which is a brochure that the Energy Institute put together, which is very nice. And then we also have kind of an interest group, H2 at UT. It's this site here. So just Google H2 at UT, and it's a list of people who are interested at UT working on hydrogen, what they do. So if you want to reach out, that's probably the best place you can go. Summary. So lots of potential there. I would say lots of potential to replace, especially natural gas, as an energy carrier. But it's not, unlike natural gas, it's not something you can get out of the ground. You have to produce it. It can be transported like natural gas. Hydrogen has the capability of getting CO2 out of the stream of what we call hard-to-abate industries, like I mentioned the steel industry, for instance. It could be used for trucking, long-distance trucking. So lots of different applications. It's still, the question is, which application will carry, which is the killer app, so to speak, to move hydrogen along. Technology development needs to focus on cost reduction. It's currently still too expensive. But we have a target of this $1 per kilogram, I guess. Storage could be one of those killer apps for hydrogen, because we don't really have other alternatives for long seasonal storage other than hydrogen. I don't see any fundamental technology barriers, really. I mean, we could do it today, and we're starting on pilots today. It's just a matter of cost at this point, but I don't see really any issues that prevent us from doing it other than cost. And in many cases, the cost comes down as you start doing it, right? Economics of scale. So the more you do it, the cost will come down. Technology development, people working on better electrolyzers, on better storage capabilities, so the cost will eventually come down. But there are still research needs, how to do it safely, how to do it cost effectively, and how to minimize impact on the natural environment, because that's the ultimate reason we're doing it. With that, I hope we have a few minutes left for Q&A from the audience, and I guess online as well.
Right. All right. Let's thank you. All right. I'll get to the room. So first, one note here: the Bureau of Economic Geology's core storage or libraries, second largest in the world. Is it the first largest in the world?
So we have three locations. We have one in here, Yankee campus. We have one in Houston and one in Midland. It may be the largest that is privately or that's public.
Yeah,
right.
Yeah,
not owned by Exxon or some other large company.
Very well. Any questions in the room?
So for those who are training graduate students in an engineering department, we've been working with CO2 and nitrogen, and everything is set up in labs. Now, if I just want to convert to hydrogen, can I use graduate students to work on that?
So the safest bet is to use hydrogen at less than 4%. Then it's safe. So, and a lot of the work that chemical reactions can be done with low concentration of hydrogen. So that's one answer. The other one is, yeah, we use hydrogen for some analytical equipment uses hydrogen, for instance. You know, so it's being used in.
So pointer on some porous media exploration by Dr. Hosseini on in BG. So they're doing experiments. I mean, they're not graduate students necessarily, but it's a safety concern.
I don't know what the training requirements are, but you guys handle flammable gases all the time. You know, it's another one.
But most people, like the conversation right now, it's like, I don't know, beginning graduate students, maybe not.
Think if you can do it at low concentrations, right? You know, and then you have no concerns.
Right. Thank you.
When it comes to the injection and the withdrawal cycles, it's different for like a porous reservoir and salt cavern.
So
Each question.
Yeah, the question is if, in terms of injection production, the caverns behave differently than the porous storage media, right? And yes, they do. The cavern is very similar to a surface tank, right? It has a defined volume. You have one well where you inject into and produce from, and you can inject and produce at a higher rate. With the porous media storage, porous media is a sand with a lot of pore space, but whatever you inject and produce has to move through the pore space around those grains and through the pore throats, and that slows everything down, right? So the injection and the production rate would be much slower, which may sound like a disadvantage because you cannot quickly recover it, but it also actually makes it safer. So part of the reason we believe caverns are less safe than porous media storage is because you get higher pressure gradients with the salt storage, and if something escapes, it escapes more quickly. So it's a pro and a con. But yes, they are different.
Here's a related question online, and you have to give some definitions best you can. The question is about storing hydrogen in embedded salt formations. Is this feasible? And it says it's seen this in England at the Teesside site. You're familiar with this? So what are the limitations of this, maybe in general and in the United States? Maybe define embedded salt.
So I mentioned that salt is, geologically speaking, likes to move around because it's buoyant, lighter than the other rock formations. So it tends to form, over geologic time scales, millions of years, it tends to form salt domes. So it's just like your lava lamp, basically, you know. So it's moving up and forms those blobs, but not in all cases. So in some cases, initially deposited by evaporation of seawater, for instance, it forms a flat lying layer of uniform thickness. Over time, it may remobilize and form those blobs. So we have both types. We have the flat layers that are uniform thickness, and we have blobs. The salt diapirs is the technical term. The salt diapirs have the advantage that we can form those slender, tall caverns. In a layered salt deposit, you may lack the height for doing this. So the main difference is that the solution mining process would be similar, but you would have to have less, you could have taller cavities in the domal salt, and in the bedded salt, it would be of much lower height. And how tall it is depending on how thick that salt layer is, right? So in terms of storage volume, it would make a difference per cavern, but you may be able to have more caverns in the bedded salt next to each other and compensate for that. So it may be more expensive to do because you need more caverns mined out, but it's doable. So it's all a function of how thick is the salt layer, and also its composition. You know, how homogeneous is it? It's just pure halite, or are there other materials in it, gypsum in it, or sand layers in it? That would all affect. But that affects both domal salt and layer salt. So it is, at the end, it's just a matter of geometry.
Right. This is a question going back to your early part of this talk on the near pure or hydrogen extraction in Mali. Is there anything particular about that site that's of note? Why it produces 100% hydrogen, or do you know?
I'm not sure that's known. Which ultimately we don't know why we don't have more of that. You know, so what's peculiar about it? It must be the rate at which hydrogen is being put into that structure, probably, and the rate at which it gets consumed by reactions. So that may be the answer to this, but why that is specifically there. And again, it's not that anybody systematically looked for this in the past. People looked at hydrogen in conjunction with known oil and gas deposits, but there was not much interest in looking for hydrogen deposits. So it may just reflect our knowledge level, you know, between those.
Questions in the room? Right, I'll go back online. I guess there's some simulations you referred to simulating hydrogen storage versus natural gas storage. And one difference, which is more migration of hydrogen. So in some senses, is that something you would expect to happen just by knowledge of geology and the molecules themselves? And ultimately, do you think that hydrogen being stored in depleted reservoirs or aquifers is going to be feasible, given any differences you know about how this works?
So yes, it is expected because it's a small molecule size, I guess, so it tends to diffuse more. and in terms of viscosity as well. So it's not surprising. The extent we can simulate this is somewhat surprising until Professor Denshad modeled this. I did not expect it to be so pronounced. It is a bit of a challenge because structures that are useful for natural gas storage may not be so useful for hydrogen storage. So it needs to be looked at side by side. The sides need to be imaged by geophysics first. So what we call a tidal trap would be better suited for hydrogen than a wide open trap. And then it depends on the well placement. So it may spread out, but then you may need additional wells to use the hydrogen back, right? So it's a function of designing it properly. Well, first finding a suitable trap that is good for hydrogen storage, then designing the well geometry and also the injection production approach to work around that. So I don't think it's a major hurdle, but it's something that needs to be factored in. Yes. Otherwise, you risk that you don't retrieve the hydrogen that you inject.
Right. Okay, yeah, we're going back.
So I heard that you are working on the risk side of the hydrogen storage. I'm just curious, like in terms of inducing earthquakes, what's the differences between hydrogen storage and CO2 storage, or like wastewater storage from those hydrofracking industry?
Good question. I love it. Because I work extensively on induced seismicity in conjunction with saltwater disposal from oil and gas production. That's a huge issue, especially now in West Texas, magnitude 5 earthquake. So yes, it's a good question, but I would say in response. So the proxy for hydrogen storage is natural gas storage. And there is very little seismic activity because people inject into reservoirs that had produced natural gas before. So in other words, they were pressurized before, then depleted in pressure, and then you put stuff back into it and build the pressure up. As long as you don't go above the initial pressure, you're fine. There's one example that really the only example I can find in Spain, offshore, they have earthquakes because they increase the pressure too much. So I think that can be handled quite well. The CCS is a different story. Well, first of all, that was depleted oil and gas reservoirs. If you're going to aquifer, you have to do proper pressure management. You may have to use some water out of it in order to keep the pressure sufficiently low. It's all about the pore pressure in the reservoir that triggers the earthquakes. The CCS, the difference here is one of scale. Hydrogen storage will always be somewhat limited, but CCS is high volumes of CO2 that needs to be disposed of. And in my view, induced seismicity could be an issue, but I don't want to step too far away from the topic of today, because otherwise someone may throw things at me.
Right. DG is the place for all of this information, though. Here's a question which you can say whether how appropriate the question is. What is the typical air volume present in these subsurface storage options? Or is that even a thing to think about? Air
there would not be any air. There would be, so this default is some type of aqueous fluid. That means water with dissolved solids in it. Brine, or in many cases, seawater salinity or more saline or less saline. So that's the default. In some cases, we have oil and gas, right? So the oil and gas will displace the water and fill the pore space to a large extent. There's always some water left. In some rare cases, we have a CO2 charge, but air, no. In the subsurface, it's either water, oil and gas, or CO2.
Okay, we'll make this a final question online here. How do you address the time mismatch between seasonal storage of hydrogen and daily energy, excess electricity from wind and solar? It's just simple as you have just incremental amounts of hydrogen that just keep accumulating in the reservoir, right? It's not like you have to store all the wind and solar all day. You
Right.
store a
So
little bit at a time.
ultimately, the economics that would dictate when hydrogen would not be suitable for short-term storage, then the injection, production, and the purification costs would be too high to make it worthwhile. So that would be the lower cutoff here. And I don't know what the answer is, and I don't know if anybody actually has a good answer for this. It may be more. I show this graphics that goes down to weeks. I'm not sure if it's economic to store hydrogen in the subsurface for weeks. In a tank, yes. In a surface tank, yes, but in the subsurface, most likely not. I would think a minimum will be a couple of months. I'm thinking more of seasonal storage for subsurface storage.
Right. Now, do like the listener, if they're still online, look at the natural gas storage data from the EIA, you can see the clear 6-month seasonal storage between winter and summer, and you're anticipating something similar.
Yeah.
Okay, so let's end it there. Thank you very much, Peter.